All right, so let's do an example where we are de-energizing a coil. Let's go ahead and start out with a source that's high and it's going to pulse low at time t equals 0. So let's say that it starts at, I don't know, let's just say 3.3 volts and pulses down to 0. And we got our resistor here and our inductor right here. And so let's make this 1 kilo ohm resistor, and let's just make this a 1 millihenry inductor. Okay, and what I want to determine in this circuit is, let's see, what is the, let's say we want to determine what is the current flowing through the inductor at time t equals let's say 2.5 microseconds. Okay, that's what we're interested in figuring out. So I'm de-energizing my coil, so of course what I'm going to be looking at is basically my current. Well, first of all, in steady state, when this value has been sitting at 3.3 volts for a long time, my current is going to be, this is going to be 0 because my inductor is going to behave like a short, and this is going to be sitting at 3.3 volts. So my current is going to be, for a long time, it's going to be 3.3 milliamps, right? And then at time t equals 0, right, my pulse down to 0, and once I pulse down to 0, that's when my current starts bleeding off exponentially. So that's what I'm going to be looking at, is this exponential bleed off of the current, right? And what I'm interested in is, we know that it takes about 5 time constants to get there, to get to about 99%. So we're going to be around here. And I want to know so let's first just determine what tau is in this example. Tau is L over R, so it's going to be 1 millihenry divided by 1 kilo ohm, which is 1 microsecond. And so at 2.5 microseconds, we're going to be at around 2.5 tau, which is going to be somewhere right in the middle, like right here. And I want to know what is my current at that point, right? That's what I'm interested in. So let's go ahead and utilize our de-energizing equation. I can go back a couple slides and find it, or I can just pull it out of memory. It's going to be that IL of t is going to be equal to my IL initial times e to the minus t over tau. Okay, so in this case, my IL initial we determined already was 3.3 milliamps. So I'm going to write that, 3.3 milliamps times e to the minus t over 1 microsecond. And so then to determine IL of 2.5 microseconds, all I need to do is plug in, sorry, not micro, milliamps, e to the minus 2.5 microseconds divided by 1 microsecond, and I can determine that current. So let me go ahead and do that. Multiply that by 3.3, and I get that IL of 2.5 microseconds is 0.27 milliamps, all right? And so that means that my current right here, let me go back to my pen. This current right here at time 2.5 microseconds is 0.27 milliamps, all right? Okay, so that does it for this example. And in the next example, I'll go ahead and solve one more de-energizing a coil example problem. And then we will be just about done with Module 4. I'll do a final recap of capacitors and inductors, the similarities and differences, and then we will be completely done with this module. So I'm so excited to get done with this module. It's probably the hardest and longest module of the class without a doubt. And so let's go right on into the next example.